In the previous lecture, we were discussing about the extension of the concept of multiplexers and how there is a possibility where we can realize functions of four variables which normally need a multiplexer of 16:1 that can also be realized with an 8:1 multiplexer, or how a three variable function which ordinarily requires an 8:1 multiplexer that can also be realized using a smaller multiplexer, that is a 4:1 multiplexer. So let us quickly take a recap of that. Suppose I have a four variable function. Suppose I have a four variable function and I would like to realize that using an 8:1 mux. So suppose I have something of this kind, the function. So as you can see, this truth table has 16 rows. So ordinarily we would require a 16:1 mux to achieve four variable logic functions. However, let's suppose there is a function which looks kind of like this. So as we had discussed that one of the ways through which we can realize this kind of functions using a smaller mux is to eliminate one variable. So therefore we can try and eliminate the d variable because it is supposedly the least significant. So therefore what we did was we isolated the d from the rest of the inputs, and what we saw was that d essentially changes after every two rows. So therefore the period of d is essentially two rows. So therefore let us divide them now horizontally in groups of two. Because the period of d is 2. Alright, so then what we did was we sort of covered the a, b and c variables, and we saw that for every period, how does y depend on d? So what we saw was that, what we see was that y is, for the first period, y is equal to d itself, because d is 0, 1, y is also 0, 1. For the second period, y is the complement of d, because when d is 1, 0, when d is 0, 1, y is 1, 0. So y becomes d bar. Then for the third period, no matter what is the value of d, y is equal to 1. So here in this case, y will be 1. For the fourth period, no matter what is the value of d, y is always 0. So over here, y will be 0. Then again here, y will be d bar. Here also, y will be d bar. here y is d, and here y is 1. Now supposing we have these, after making these groups of 2, what we see that y can now take 8 possible outputs. So therefore, for each group what we see is that the value of a, b and c are fixed. So for the first period, a, b and c are 0, 0, 0. For the second period, a, b, c is 0, 0, 1, and for those cases y has a unique output. So therefore, we can condense this truth table into a 3-variable function. So when a, b and c are 0, 0, 0, y is equal to d. Then we have d bar. Then we have 1, then we have 0, then d bar, d bar, d and 1. So therefore, we now have 3 select inputs. And each of these 8 possible outputs can be used as the data inputs. So therefore, we can use an 8:1 mux. So the way to realize it is now very simple. So if this is our 8:1 mux, so the select inputs will be a, b and c. Now there will be 7 data inputs, d0, d1, d2, d3, d4, d5, d6 and d7. So if we quickly refer back to our old truth table, so d0 will be nothing but d, d1 will be d bar, d2 will be 1, d3 will be 0, this will be d bar, d5 will be also d bar, d6 will be d, and d7 is 1. So with this 8:1 mux, the output here will be y. This is a recap of what we had done in the previous lecture. If I recall correctly, the previous lecture we had seen the example of implementing a 3-variable function using a 4:1 mux. Today we took one step forward, that is the implementation of 4-variable functions using 8:1 mux. Note that these d0s and d are not the same. d0 just means the data input, where d is one of the input variables. Now suppose we ask that we have a 4-variable logic function. We know how to implement it using an 8:1 mux. But before we talk about that, one thing I forgot to mention is the enable. So if the enable is active high, this must be given 1. So coming back, we know how to implement a 4-variable logic function using an 8:1 mux. However, suppose for some reason that 8:1 mux are not available. What we only have is the 4:1 mux. Now the problem becomes a little bit more serious. How can we implement a 4-variable logic function using a 4:1 mux? So let's take the same function which we took just now. So 4:1 mux has two select inputs. So that means again we have to keep two of these variables and eliminate two. So therefore we can eliminate now C and D. If you look at C and D, they are repeating after every 4 rows. So now what we will do, we are isolating C and D anyway from A and B. Alright. So what we will now do is that, okay, first let me fill up the Y column. So now what we will do is that for every period of C and D, that is after every 4 rows, we are going to draw a line. Notice that after every 4 rows, CD combinations are repeating themselves. Alright, now what we will do is we will cover A and B and express Y as a function of C and D only. Alright, so what you can see is that now Y will become a 2 variable function. So for this period, Y will be equal to what? You can see that Y is nothing but the XOR function of C and D. Assuming that all the gates are available to us. For the second period, what will be Y? So we can very quickly draw a K-map. So this is A, this is B, A bar, C and D. C bar and C, D bar and D. 0, 1, 2 and 3. The minterms are here and here. So I can just make a group of 2 and find that this is C bar. So Y in this case will be C bar. For the third period, you can very easily prove that Y will be equal to D bar. So earlier the minterms were 0 and 1, now it's 0 and 3. Sorry, 0 and 2, they'll be here and here, which will correspond to D bar. And over here, Y will be equal to the OR function, that is C plus D. So if I have a 4:1 mux, these two will be my select inputs. A and D will be my select inputs. And each of these Y's will go to my data inputs, D0, D1, D2 and D3. Why? Because notice that for every period, again, the values of A and D are fixed. For the first period, it's 0, 0. Second period, it is 0, 1. Third period, it is 1, 0. Fourth period, it's 1, 1. So if I now write a truth table of A, B and Y, so for the first case 0, 0, Y will be equal to C XOR D. Here it will be C bar. Here it will be D bar. Here it will be C plus D. So we can now draw the 4:1 mux. This is Y. 2 select inputs A and B. 4 data inputs D0, D1, D2 and D3. So D0 will be the XOR combination of C and D. This will be C bar. This will be D bar and D3 will be the OR combination of C and D. As simple as that. Suppose this one has a active low enable, then in that case we will connect it to ground. So this is how you can implement large number of variables using smaller size muxes. Similarly, if you now had to do it using a 2:1 mux, then you would eliminate B, C and D, and A would be the only select input remaining. What we are also noting is that as the mux size becomes smaller and smaller, while the number of input variables don't change, the logic for the data inputs start becoming more and more complex. In the earlier case, when we could realize using 8:1 muxes, we need D bar, D bar, so we need NOT gates. Then when we essentially made the problem more serious, we reduced it to a smaller mux, that's a 4:1 mux. We need NOT gates here, we need XOR gate here, we need OR gate over here. So if you start making the mux size smaller and smaller while the number of input variables for the function don't change, then in general the logic for the data inputs would essentially become more and more complex. So what did we see so far? We saw that supposing we have a logic function of some number of variables, of a certain number of variables, but we don't have a mux with select inputs of that many variables equal to the inputs variables for the logic function. Then we can indeed realize the logic function using another smaller but a single mux. Of course, there will be some additional logic circuitry that is necessary. Now, let us sort of rephrase the question. Let us say that I have a 4 variable function, but I don't have a 16:1 mux. So far, the problem is the same as before. I have a 4 variable logic function and I do not have a 16:1 mux. But I want to implement this using 8:1 mux. However, there is no constraint on the number of 8:1 muxes that I can use. There is no constraint on the number of 8:1 muxes I can use. That means I am free to use more than one 8:1 mux. So in that case, how would we do it? Let's formulate it. Number of variables in the input are again 4 and there is one output. So let us say I want to realize 4 variable logic functions. Using 8:1 mux. So I can use more than one mux. That's why I put ES plural in bracket. Now, in an ideal world, if there was no constraint on the number of 8:1 muxes, how many muxes would we need? Result tells me I will need 2 muxes. Why? Because each 8:1 mux consists of data inputs. And a 4 variable logic functions has 16 rows. So therefore, if I have 2 8:1 muxes, I could totally have 16 data inputs. In total. So therefore, what can I do? Let us say I have these two 8:1 muxes. So each of them have D0, D1, D2, D3, D4, D5, D6 and D7. So totally I have 16 data inputs. I have 16 data inputs. So let me draw the truth table over here for this function. Let us say I'll keep it the same as before. All right. So the output is this. Right? So let us say that without worrying so much about what the input variables are, here there are 16 rows or 16 data inputs. So let us try and keep things simple. Normally, if we had a 16:1 mux, we could feed the data inputs right from D0 to D15 with values in this order. So therefore, let us say we will do exactly that. So D0 will be 0, D1 is 1, D2 is also 1, D3 is 0, then 1, then 1, then 0, then 0. So we have stopped over here. With this, the first mux ends. Now after this line, the second mux starts. So here I will put 1, 0, 1, 0, then 0, 1, 1, 1. So in some sense I can say that this is, I'll call it as M0 and I'll call this as M1. That is mux number 0, mux number 1. So these go to M0 data inputs. And these are for M1 data inputs. Now the question is, each of these muxes will have 3 select inputs. What will they be connected to? What will they be connected to? More importantly, each of the mux has one output, but finally I need a single output Y. Right? There must be some kind of a logic that is required. Okay, so then coming back, what we said was up until here, these are the data inputs for mux 0, and after this line, these are the data inputs for mux number 1. So we had made a thin line over here. Let us extend that to the input side as well. Now what we are seeing? What we are seeing? We see that there are 8 possible outputs or 8 possible data inputs for each mux. So therefore, let us see if these 8 outputs or these 8 rows correspond to a 3 input truth table. Now if I cover the A column, what I see is that y is now a function of b, c and d. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 all the way till 1, 1. So therefore it is like saying these would act as data inputs for this M0 8:1 mux if the select inputs were B, C and D. So therefore I will put B, C and D over here. Likewise, let's go below. For these 8 outputs, these 8 possible rows, again we are seeing B, C, D are changing from all zeros to all ones. So therefore, if we are looking at this mux M1, which is an 8:1 mux, this would be able to act independently if the select inputs were again B, C and D. Alright? Alright? Yes. Now, we have sorted out the select input problem. The question now is, what will happen to y? And where does a feature? So far, we have not talked anything about a. But we cannot simply brush a under the carpet because ultimately the function y is a 4-variable function, not a 3-variable function. So therefore, these output y, we will call this as y1. Or sorry, let's call this as y0. This is y0. And these 8 outputs, we'll call it as y1, which are the outputs of the individual muxes. Now notice one thing. For the first 8 rows, the value of a is 0. And for the last 8 rows, the value of a is 1. So therefore what I can do is I can use a in the enable logic. When the output could be anything among the first 8 rows, then M0 must be active, M1 must be inactive. And when the output can be anything among the next 8 rows, M1 must be active, M0 must be inactive. So therefore, if I have an enable which is active high, what should be the function? Can I have this enable that is controlled by a? So when a is equal to 1, what we notice is that a now becomes a unique identifier for each of these first 8 rows and the next 8 rows. So for the first 8 rows, a is 0. So when a is 0, M0 must be activated. And if my enable is active high, then my a should be given to the enable through a NOT gate. Because if a is 0, then this output will be a 1. Likewise, when a is 1, the second mux has to be enabled. So therefore, this will be again, without a NOT gate, it's simply a. So I am now using a very cleverly to control the enable. Now this is where you see the enable is actually playing a role in making each mux active inactive. So in the previous lecture when we were discussing enable, we thought it is just another input which does not seem to have much of a value. But here we can see that we can indeed integrate this enable input with one of our logic inputs. Alright. So we have now seen how to use a to make each mux active. So therefore when the upper mux is active, whatever be the value of y0, it will be anything out of these 8. But one thing we can say is that when m0 is active, m1 will be inactive. Therefore, the y1 will be equal to high impedance. Conversely, when m1 is active, y1 will be anything out of these 8 inputs, any one of them. But one thing we can say is that m0 will be inactive and y0 will be equal to the high impedance. Is that fine? Now, the question is, we have y0 and y1. What will be y? How can we combine these two? One thing we are immediately seeing is that at a given time, any one out of y0 and y1 will be a high impedance value. So therefore, what I can do, I can use an OR gate to combine. So if y1 is equal to high z, then y will be equal to y0 plus y1. So high impedance, if you OR it with any y0, the answer will be y0. And if y0 equals high z, then y will be equal to y1 plus y0, where y0 is a high impedance, so this will be equal to y1. And this is what will happen. It's kind of like an open circuit. Now, there is a simpler way with which we can realize this OR gate. We don't actually have to use an OR gate. Why should we use one more gate when we can achieve a choice of y using y0 and y1? So let's draw this all over again. So again we have D0, D1, D2, D3, D4, D5, D6 and D7. Also we have D0, D1, D2, D3, D4, D5, D6 and D7. So zero, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So we had this enable over here, which is a function of a bar to be precise, and here the enable is nothing but a. The select inputs are B, C and D for each of these masses. This is M0, this is M1. Now the output over here is Y0, the output over here is Y1. What I can simply do now is I can connect these two together and call this as Y. If you look at it electrically, if Y0 contains an output, that is if M0 is active, the Y1 will be a high impedance. So therefore this will behave like an open circuit. So whatever is the voltage at Y0, same will be the voltage at Y. Likewise, when M1 is activated and M0 is deactivated, Y0 will be an open circuit or a high impedance. So whatever is the voltage at Y1, it will be the same in parallel with Y0, and that is equal to Y. So this kind of connection, where we are essentially replacing the OR gate, this kind of connection is called as a wired OR. Wired OR connection. Now, there is one more way. There is one more way in which we can achieve this. There is one more way through which we can achieve this. But in that case, what we can do is we can keep both of the multiplexers enabled together. So therefore, suppose again I have these two muxes. Again, we have D0, D1, D2, all the way till D7. This time I will not show all the connections. The connections remain the same as before. This is M0. The select inputs are B, C and D. This is M1. Select inputs are B, C and D. Now what I will do, I will make enable connected to 1 for both of these muxes always. Now comes the fun. We have Y0 and we have Y1. Again, what we are noticing is that we are not using A here so far. Now each of these are 8:1 muxes. Suppose it is now told to us we can use any mux in any number but not 16:1. So therefore what I can do, I can use a small 2:1 mux. And it will have two data inputs D0 and D1. So I will connect Y0 and Y1 over here. And 2:1 mux has one select input and I will connect to that A. And this will be my final Y. Now why is that? Why am I doing this? If you go back and look at the truth table that we had earlier defined, you see that for A equal to 0, all of these 8 values are possible. And we have called this as Y0. And when A is 1, all of these values are possible and we have called it as Y1. So therefore, whatever be the logic function Y0, whatever be the logic function Y1, we can use these as two inputs if A is given as a select input for the 2:1 mux. So here we saw essentially a way through which we can realize the function of the OR gate using a 2:1 mux. Right? So let's write it again. So when A and Y, when A is 0, Y will be equal to Y0. And when A is 1, Y will be equal to Y1. Now, suppose we want to actually put a number over here, or we want to actually quantify the stuff. So Y0 is some function of B, C and D, and Y1 is some function of B, C and D. So I can say that Y0 is some function F0 of B, C and D, and Y1 is some function F1 of B, C and D. Whatever they mean, those same functions, the inputs are given over here, inputs are given over here. So this Y0 will be F1 of B, C and D, and this Y1, sorry, this will be F0. This will be F1 of B, C and D. If you want to actually quantify, there is a way through which you can quantify. You can rewrite the truth table. So you can say, right now I'm not writing, let's not write A right now. Let us treat each of these as two individual truth tables as functions of B, C and D. So therefore for Y1, or let's say for Y0, there will be one table. For Y1, there will be one table. So we will now split up the truth tables. So 0, 0, 0, 0, 0, 1, 0, 1, 0. So y0 was this, and y1, whatever the same B, C and D, this was 1, 0, 1, 0, 0, triple 1. So you can actually construct two K-maps for each of the output variables. This is D bar and D, B bar, C bar, B bar, C, B, C and B, C bar. So the minterms will be 0, 1, 1, 0, 0, 1, sorry, this is 1, 1 and 0, 0. That's it. So I can make a group over here. This is group number 1. I can make one more group this way, and this will be left behind. So y0 will be BC bar plus C bar D plus B bar C D bar. And y1, we can construct a K-map for this also. So this will be 1, 0, 1, 0, 0, 1, 1, 1. So over here, we can make this group, and this group. So therefore, what we are seeing is, in this case, y1 will be equal to B bar D bar plus C D bar plus BD. That's it. So likewise, you can construct virtually any number of logic variables for a function using any multiplexer or any smaller multiplexer. So in this lecture, we saw the means through which we can build up on our concept of being able to realize big logic functions with small multiplexers. First, we saw how we can realize using one small mux, and later we saw how we can realize big logic functions using multiple smaller muxes, and one of those ways was through which we can use the enable input of each of the smaller muxes that is driven through one of the logic inputs. We also saw later on how we can combine the outputs of each individual mux to realize the final output of the logic function that is required. We saw we could use an OR gate, we could use something called as a wired OR, and we could also use a smaller mux to choose the output, or to choose the intermediate output values to be given as the final output. So we shall continue our discussion on MSI circuits in the next lecture. Thank you.